Okay, today we are introducing waves. So, what is a wave? Well, a wave is just something that transfers energy and information from the source to an observer. And the important thing to remember is that the waves do not transfer matter. For example, ripples on a water surface. So ripples are an example of waves, and the wave itself travels, but then have a little think about a bird or a leaf on that water. Those just bob up and down. They don't move with the wave. That's because the wave travels through the water particles and doesn't pick all that water up and take it with it. If waves did transfer matter, every time somebody made a sound, the air particles around my hand would move away from my hand, leaving a vacuum, which doesn't happen. You need to know some of the features of waves. For example, amplitude. This is the distance from rest or equilibrium to the maximum displacement of your wave. Note that this is this distance here and not that total distance there. That's a very common mistake for pupils in exams. Next, how about wavelength? And that is the distance between two identical points on a wave, such as crest to crest or trough to trough. But it could be any two identical points, like this point here and this point here. Just be careful. Here are 2 points that both lie along the equilibrium position. However, the distance between these 2 points is not the wavelength. That's because they're not actually identical points. One is about to go up in the pattern and the other is about to go down in the pattern. Okay, you also need to be able to define frequency. Frequency is the number of waves passing a point per second. So if you watch ripples on some water, your frequency would be the number of crests passing you every second. We measure frequency in hertz. Time period. Your time period of the wave is the time for one complete oscillation. So for example, if you're a bird on a water, that is the time for the bird to bob from their rest position up, down, and back to their rest position again. Sometimes it is useful for us to draw wave fronts instead of waves like this. If I take this wave and convert it to a diagram of wave fronts, I get this picture where the distance between each of these lines is one wavelength. Kind of like if you took a bird's eye view of water waves, it would look a little something like this, stripes. Now, you have 2 different types of waves that you need to know about: longitudinal and transverse. And the best way to show this is with the slinky. I'm down on the floor with my slinky. What I've noticed is, firstly, my floor is in desperate need of a hoover, but also moving the slinky makes a lot of noise. Anyway, let's push through that and let me show you a longitudinal and transverse wave on a slinky. Okay, so for a transverse wave, the direction of vibration, or the direction that my hand moves, so from the left to the right of the screen, is perpendicular to the direction of wave travel, which will be from my hand to the top of the screen, like this. Okay, however, for a longitudinal wave, my direction of vibration, so this time I'm going to move my hand up and down, is going to be the same or parallel to the direction of wave travel, like this. On my longitudinal waves there, you saw bits of the slinky that clumped together and bits that were spaced out. Those are called rarefactions and compressions. And again, the distance between 2 identical points, like the middle of a rarefaction and another rarefaction, is the wavelength of my wave. Okay, hope you found that helpful. If you did, please do give us a like and subscribe. Make sure to download the notes for all those key features of waves. Thanks for watching.